You've heard it your whole life, nothing can go faster than light, as if that makes the universe feel manageable. But here's the twist. For a cosmos this huge, light is actually embarrassingly slow. It takes more than 4 years just to reach the nearest star, 100,000 years to cross our own galaxy, and most of the universe is so far away its signals will never reach us at all. In this video, we're going to break down how the ultimate speed limit turns the universe into a laggy, unreachable maze, and why almost everything that exists is permanently out of your reach. But before we continue, please subscribe to the channel to give your support. Let's continue. You'll learn that nothing can go faster than light, about 300,000 kilometers per second, around 186,000 miles per second, more precisely 299,792,458 meters per second. Those are big numbers. And yes, at that speed, light could go around Earth about 7.5 times in 1 second. That sounds unbeatable, almost perfect. But your brain is used to planet-sized problems, flights, road trips, maybe the distance to the moon. The universe does not care about those scales. It works in light years, megaparsecs, and billions of years of expansion. And on those scales, this ultimate speed is not impressive. It is a hard limit that makes almost everything in the universe permanently out of reach. So the first question you need to ask is very simple. When you say 1 second of light, what distance are you actually talking about? A light second is just the distance light travels in 1 second, roughly 300,000 kilometers, about 186,000 miles. That sounds huge if you think in road trips or plane flights, but compare it to the distance from Earth to the moon. On average, about 384,000 kilometers, or 239,000 miles. Suddenly, 1 light second is not enough. Light needs about 1.28 seconds to get from Earth to the moon. Even the fastest signal in the universe cannot clear your local neighborhood in a single second. That means when you say something like, this happens in under a second, in space terms, that is already slow. You are still inside the Earth-Moon system. You have not even left the tiny bubble around your planet. The unit we use to brag about how fast light is instantly exposes how limited our local patch of space really is. So if 1 second of light barely gets you past the moon, what happens when you stretch that time? How far does your normal sense of speed fall apart compared to light? Take a standard passenger jet, cruising around 900 kilometers per hour, about 560 miles per hour, good enough to cross continents. Now compare it to light, which does 300,000 kilometers every second. That's 300,000 kilometers in 1 second, versus 900 kilometers in 1 hour. It is not even close. Here's a clearer comparison. Ask how long a jet would need to cover 1 light day, the distance light travels in 24 hours. Light does that in a single day. The jet, at 900 kilometers per hour, would need well over 50 years of continuous flying to cover the same distance, more than half a human lifetime just to match what light does while you sleep and go to work a few times. And that still sounds like light is winning. But now stack that against 1 light year. 1 light year is about 9.5 trillion kilometers, roughly 5.9 trillion miles. That's 9.5 million billion kilometers. A light year is 365 light days. So now your 50 plus years per light day turns into tens of thousands of years per light year for the jet. And suddenly light itself starts to feel slower than you expected, because even at the top speed of the universe, a single light year is already a big commitment. So the obvious question is, if light is so fast next to jets and rockets, why are we calling it pathetically slow in the first place? Slow compared to what exactly? Compared to human machines, light is untouchable. Your fastest spacecraft move at tens or maybe a few hundred kilometers per second. Light does 300,000 kilometers per second. Your rockets are crawling, but the universe is not built to match your engines. It is built on scales where 100,000 light years or a billion light years are normal distances. The observable universe is about 93 billion light years across. That means if you had a perfect beam of light fired from one edge straight to the other, it would still take tens of billions of years to cross. And that's ignoring the fact that the universe is expanding while the light moves. 300,000 kilometers per second sounds huge only because your everyday distances are tiny. Once you compare it to a universe this wide and this old, it's clearly not fast enough to tie everything together. And this is where things get uncomfortable, because the speed of light is not just about travel, it also controls how fast information can move. So you're not just dealing with slow trips, you're dealing with a slow reality. Every signal, every update, every change in the universe is limited by this same speed. Light, radio waves, gravity changes. All of it is capped at that 300,000 kilometers per second. It's not a suggestion. It's a hard rule of space-time. So when something happens far away, you don't find out right now. You only find out once light has carried that information to you, however long that takes. Think about a star 1,000 light years away. If that star collapses or explodes today, from its own point of view, you won't see that event for 1,000 years. Nobody on Earth, no telescope, no satellite can jump ahead of that delay. You are locked into waiting for light to arrive. The universe you see in the sky is always late. You are not seeing what is happening. You are seeing what finished happening, sometimes millions or billions of years ago. So your entire picture of reality, everything you see when you look up, is more like a history archive than a live feed. And it's not late by a few seconds, it's late by enormous stretches of time. On cosmic scales, this delay is so big that most of the universe will never be part of your now, no matter how long you wait, because the light either hasn't had time to reach you or never will due to expansion. That's why calling the speed of light fast is half the story. Yes, it's the fastest speed possible, but it's also the reason your access to the universe is narrow and delayed. The same rule that protects causality, that keeps cause and effect in order, also traps you inside a tiny bubble of influence and information. So here's the real tension building underneath all of this. If light is already too slow to give you a live view of distant stars, what happens when you stop thinking about distant galaxies, man? Instead, just try to talk to something very close by. Not another star, not another galaxy, just the one thing in space you think of as right next door, the moon. Talking to the nearest thing in space, the moon, already feels like dealing with a built-in lag spike, and that's what the fastest speed allowed by physics. The moon is only about 384,400 kilometers away from Earth, roughly 238,855 miles. That is close. In solar system terms, that is your front porch. At light speed, a radio signal or a laser beam takes about 1.28 seconds to go one way. So when the Apollo 11 astronauts spoke from the surface, their words left the moon at light speed, crossed that 384,000 kilometer gap, and reached Earth a bit more than a second later. You hear the answer, you respond, your reply then takes another 1.28 seconds to get back. Total round trip, roughly 2.5 seconds. And that delay is not compression, not bad hardware, not a server problem. It is pure physics. Even with perfect technology, you cannot get a live, instant back and forth with people on the moon. You would call a 2.5-second delay on a voice call a terrible connection, but that is the best the universe will ever give you for Earth-Moon chat. So if talking to something a few 100,000 kilometers away already feels like a slightly broken call, what happens when you look at the thing that powers your whole planet? The sun. The sun is much farther, about 150 million kilometers away, around 93 million miles. Light covers that distance in about 8 minutes and 20 seconds. So every time you see the sun in the sky or feel its warmth on your skin, you are not feeling the present. You are feeling what the sun was doing more than 8 minutes ago. This delay isn't just for light. In general relativity, changes in gravity also move at the speed of light. So if, in a purely hypothetical scenario, the sun were to just disappear right now, no warning, no slow fade, Earth would not know immediately. You would still see the sun in the sky for over 8 more minutes. Earth would continue in the same orbit, following the same curved path in space-time, and only after those 8 minutes and 20 seconds would the darkness and the gravitational change arrive together. That means your now is already offset from the true state of your own star, the thing that sets your days and seasons. When people talk about living in the present, in a strict physics sense, your present is always slightly wrong, even inside your own solar system. And if your own star is 8 minutes in the past, what happens when you go farther out to a planet humans want to explore for real? Mars. Mars orbits the Sun at a different distance than Earth, and both planets are moving, so the distance between Mars and Earth keeps changing. At its closest, Mars can be around 55 million kilometers away, about 34 million miles. At its farthest, when they are on opposite sides of the Sun, the distance can be over 400 million kilometers, roughly 250 million miles. Light and radio signals take between about 3 minutes and roughly 22 minutes to travel one way over those distances. So if engineers on Earth send the command to a Mars rover, that signal might arrive in as little as 3 minutes or as long as 22 minutes depending on the alignment. Then the rover carries out the instructions, sends back data, and that reply takes another 3 to 22 minutes to get home. You cannot sit at a joystick and drive a rover like a remote control car. By the time you see the result of one action, it is already many minutes old. So mission teams send carefully planned sequences of commands, like a batch of emails, not instant messages. That is the reality of talking to another planet inside your own solar system. You are working with built-in awkward pauses. Every move is delayed. You never see what is happening in real time. You only see what happened several minutes ago. And if Mars already forces you into this slow, delayed conversation, what happens when you stop dealing with planets and start dealing with the edge of the solar system itself? Take Voyager 1, a spacecraft launched in the 1970s, now well past the outer planets, out in interstellar space. It is more than 24 billion kilometers from Earth. That's tens of billions of miles out, completely beyond the orbits of the giant planets. At that distance, a radio signal traveling at the speed of light needs over 22 hours to get there one way. So when a message leaves Earth aimed at Voyager 1, for almost an entire day, that signal is just crossing empty space. By the time it reaches the spacecraft, Voyager 1 has continued moving on its path. When the probe responds, its reply then spends another 22 plus hours coming back to Earth. The data you receive describes the state of the spacecraft as it was roughly a day earlier. You never talk to Voyager now. You are always talking to where it was yesterday. That is what real time looks like when distances hit tens of billions of kilometers. Every command, every status update is locked behind a time wall measured not in seconds or minutes, but in hours. And remember, this is still inside what we casually call the sun's backyard. The distances inside your solar system are nothing compared to the distances between stars. But even here, light is already slow enough to turn every interaction into delayed messaging. So put the pieces together. Seconds of delay to the moon, the closest major object in space, minutes of delay to Mars, the planet humans actually want to land on and maybe live on, hours of delay to a spacecraft that has just barely stepped outside the main planetary region. These are not exaggerated numbers. These are simple results of distance divided by the speed of light. And here's the key point. All of these delays are tiny when you compare them to the distances between stars, or across your galaxy, or across clusters of galaxies. The solar system is small, but it already breaks your intuition for instant and live. If the speed of light is already annoying when you're just trying to talk across a few 100 million kilometers, what happens when your nearest star beyond the sun is more than 4 years of light travel away? The nearest star beyond the sun is so far away that even at the absolute maximum speed allowed by physics, it is still a multi-year one-way trip, and that is your best possible case. Proxima Centauri, your next-door star, is about 4.24 light-years away. That means light, moving at 300,000 kilometers per second, has to run nonstop for more than 4 years just to get there, in straight-line vacuum conditions, no slowing down, no stops. In regular distance units, that is roughly 40 trillion kilometers, about 25 trillion miles. When you hear trillion, your normal sense of distance basically stops working, but that is what counts as nearby on a star map. If you could somehow ride a beam of light, leave Earth at age 20 and head straight to Proxima Centauri, you would arrive more than 4 years older. Still in your 20s, yes, but that is just to get to the closest star. Not the center of the galaxy, not a distant cluster, just the very first star outside your own solar system. Light speed doesn't make the universe small, it just makes next door sound like see you in a few years. So, if the perfect theoretical maximum speed of the universe takes years just to touch the nearest star, what happens when you use real hardware, the actual spacecraft you can build and launch? Right now, the fastest spacecraft humans have ever flown is in the range of the Parker Solar Probe. When it dives close to the sun, it can reach around 200 kilometers per second. That's roughly 125 miles per second. For comparison, that is way beyond any rocket you normally think about. It is thousands of times faster than a commercial jet. It is extreme by human standards. But set that next to light, which does 300,000 kilometers every second, and suddenly 200 looks tiny. 200 divided by 300,000 gives you about 0.0007, or 0.07% of light speed. Not 1%, not half a percent, a tiny fraction of a percent. At that speed, if you sent a probe towards Proxima Centauri, you're looking at travel times on the order of 6,000 years to cover those 40 trillion kilometers, even ignoring fuel, navigation, and everything else. 6,000 years ago, there were no modern nations, no modern science, no electricity. Entire civilizations have risen and collapsed in less time than that. So a realistic interstellar trip at our best current speed is not a mission. It is a timeline that outlives cultures, languages, probably species. Your starting society and your arrival society would not recognize each other. And that's with a tiny, uncrewed probe falling into the sun's gravity well to squeeze out speed, not a giant ship carrying people, life support, and shielding. Add that mass and engineering difficulty, and your practical cruise speeds are likely even lower. So, if your best technology can barely nibble at the edge of the nearest star in thousands of years, does cranking up the speed with future tech actually fix the core problem? Say you get very optimistic. Somehow you build a starship that can cruise at 10% of the speed of light. That's about 30,000 kilometers per second, around 18,600 miles per second. Way beyond anything real today, but still fully sub-light. No warp drive, no magic, just extreme engineering. At that speed, 1 light year takes about 10 years of travel time in the rest frame, because you're going at 1/10 of light speed. So multiply that by the size of the Milky Way. The stellar disk of our galaxy is roughly 100,000 light years across, side to side. So at 10% of light speed, crossing it would take about 1 million years. 1 million years just to go from one edge to the other. That is not a round trip. That is not a survey of every star. That is simply crossing the disk once. Even for a purely robotic probe, that timescale is extreme. Even at full light speed, no delays, a photon takes 100,000 years to cross the galaxy. That number alone tells you how bad the situation is. Light, the ultimate speed, needs longer than your entire species has existed in anything like its current form just to go from one side of your own galaxy to the other. At 10% of that, you multiply the pain by 10. On these scales, light is not fast, it is barely adequate to connect nearby regions, and completely useless for any idea of a unified live galaxy. So if moving physical ships between stars turns into a 100,000 or million-year project, maybe you think, fine, skip the ships. Just send signals, send radio messages. That should be easier, right? Radio waves are just low-energy light. They also travel at the speed of light in vacuum. So take a simple case. Suppose there's a hypothetical civilization 1,000 light years away, in some other part of the galaxy. If you send them a broadcast today in your current year, that signal will arrive 1,000 years in their future. If you're in the year 2026, they receive your hello in the year 3026. That is their first contact moment. If they answer right away, no delay, they beam a reply back at light speed. That answer arrives here in the year 4026. The total round trip for a single exchange, 2 sentences, is about 2,000 years. That is not a conversation. That is not even letters. That is trading archaeological artifacts. Maybe not even the same species on either end. A chat at that distance spans entire historical eras. And that is only 1,000 light years. Your galaxy is 100 times wider than that. So any idea of a pan-galactic chat room or a real-time network immediately dies on the basic math of distance divided by light speed. The universe lets you talk, but it forces you to do it on timescales closer to geology than to human attention spans. And there's another consequence that is easy to miss and very important. If every signal is this delayed, then nobody, anywhere, is ever seeing anyone else as they are right now. There's no common present across interstellar distances. Because light takes time to travel, every star system sees every other star system as it used to be, not as it currently is. If 1,000 light years away has a super advanced telescope pointed at Earth right now, they don't see your cities, your satellites, your internet. They see Earth from about 1,000 years ago. They see a planet in the era of the late first millennium, around the time of early medieval kingdoms and Viking voyages. Our modern world is still hidden from them for centuries. Scale that up. At 10,000 light years away, they see Earth during the last ice ages and early human migrations. At 100,000 light years away, nobody sees you at all yet. Your entire recorded history is compressed into a tiny shell that hasn't had time to reach most of the galaxy. And the same thing is true in reverse. The light you see from distant stars and possible civilizations is their old footage, their past, not their present. So the universe, as seen through light, is like a network where no node ever has live data on any other node. The farther out you look, the further back in time you're forced to look. Your now is local. It covers your neighborhood, your solar system, maybe your nearby region of space, but not the galaxy, not the universe. There is no single universal present tense, only overlapping bubbles of outdated information. And if just 1,000 light years of delay already breaks your sense of now, the obvious next question is, what happens when you stop thinking about single stars altogether and instead look at the full scale of the Milky Way galaxy, 100,000 light years wide, and ask whether anything, even light itself, can ever truly make it feel like one connected place? If the nearest star already costs you years at light speed, what happens when you scale up to the entire structure you live inside, the Milky Way itself? The disk of the Milky Way is roughly 100,000 light years across, maybe more. That means if a beam of light left one edge and headed straight across the disk, even in perfect vacuum, it would need about 100,000 years to reach the other side. Not 1,000, not 10,000, a full 100,000 years of continuous travel at 300,000 kilometers per second, about 186,000 miles per second. Homo sapiens as a species has existed for something like a few 100,000 years, so one single galaxy-wide light trip is already comparable to a huge chunk of your entire evolutionary story. If someone on one edge of the galaxy switched on a perfect flashlight toward the other edge, by the time those photons arrived, entire branches of intelligent life could have appeared, changed, then maybe vanished. And that is what the fastest possible speed baked into space-time. So if crossing the galaxy at light speed is that slow, what about just staying where you are and rotating? How does your own star move inside this huge disk? Your sun is not sitting still. It orbits the center of the Milky Way at roughly 220 kilometers per second, around 137 miles per second. That sounds extreme, but compare it again to light's 300,000 kilometers per second, and you are back at around 0.07% of the speed of light, the same tiny fraction you saw with the fastest probes. Galactic orbital speeds are high, but they do not come close to c. At that speed, one full orbit of the Sun around the galactic center takes on the order of 225 to 250 million years. So in the time since the dinosaurs lived, the Sun has completed only about one orbit, less than 2 full circuits. The orientation of the galaxy on the sky was different in their time. They looked up at a Milky Way arranged differently than the one you see now. That kind of timescale shows how irrelevant light's ultimate speed can feel on the level of whole galaxies. Gravity and orbits unfold on hundreds of millions of years. The fact that nothing can go faster than light does not make these processes feel any quicker. It just sets the rules for how information about them spreads, and that spread is still painfully slow. So, what if you try to actually cross the galaxy, not just orbit a bit inside it, and you were allowed to use the maximum possible speed, exactly the speed of light? Even then, crossing 100,000 light years takes 100,000 years in the rest frame. That number does not change. If some advanced civilization had launched a photon ship toward the opposite side of the Milky Way 20,000 years before your last major ice age, those photons would only be arriving around now, in your current era. That is with no detours, no gravitational bending, just a straight path drawn on a textbook diagram. On human timescales, on the scale of countries, cultures, and individual lives, that crossing time is effectively infinite. Nobody who starts that journey will ever see the end of it. No institution lasts long enough to track it in real time. The Milky Way is not a thing you cross. It is a background structure that stays far larger than anything you can plan for. If even light itself takes 100,000 years to go side to side, then what about the signals you have actually sent, the ones leaking out from Earth since you started using radio technology? Humans have been broadcasting strong radio signals into space for a bit over 100 years. Old TV transmitters, radar, communication systems, all of that power radiates outward at the speed of light. That means the radio bubble centered on Earth has a radius just over 100 light years. Anything inside that bubble has, in principle, had the chance to notice that something noisy and technological turned on here. Now, compare that to the galaxy scale. A radius of 100 light years inside a disk 100,000 light years across is only 0.1% of the radius. The volume comparison is even worse. It's a tiny sphere inside an enormous system. Almost every star in the Milky Way is outside that bubble, completely untouched by your signals. Not because you're quiet, you're actually very loud by natural standards, but because light is slow and you haven't been transmitting for long enough. So most of the galaxy has absolutely no idea that Earth exists, that humans exist, that your technology exists. And even if some distant region is broadcasting too, their own bubble is also small. There's a good chance your bubbles don't overlap yet. You could both be shouting into the dark, separated by thousands of light years and thousands of years of waiting. If that's how bad it is for just one small, noisy planet, what does it look like for an entire galaxy trying to act as a connected system? Is a galactic civilization even compatible with these delays? From one side of the Milky Way, reacting instantly to something happening on the other side is impossible, even at light speed. Information can only arrive tens of thousands of years late. Say there's a disaster, a star going unstable, or a threat, a gamma-ray burst source lighting up. By the time a warning signal crosses 20,000 or 50,000 light years, whatever happened is already long over. The region that sent the message might have totally changed, biologically, even physically. Any civilization spread out over tens of thousands of light years is forced to live with latency so extreme that current events on the far side of the network are basically ancient history by the time you hear about them. A policy decision, a war, a scientific breakthrough, all of it becomes a time capsule, not a live update. You don't coordinate in real time, you just exchange records of what your part of the galaxy used to be like. So at the galactic level, the Milky Way is a latency hellscape. Light is the moderator that keeps causality intact, but it's also the reason nothing across that entire disk can ever truly share the same now. And if that's already the situation inside one galaxy, the next question is obvious. What happens when you zoom out again to the full observable universe, which is billions of light years across, and ask whether light can keep up with expansion at all? The universe is only about 13.8 billion years old, yet the part you can in principle see has a radius of about 46 billion light years. That sounds wrong on first pass. If light has only had 13.8 billion years to travel, how can anything be 46 billion light years away? The reason is that while light has been moving, space itself has been stretching. A photon that left a distant galaxy billions of years ago has been chasing a target that is sliding away the entire time. As that photon crosses space, the distance between you and the source keeps growing. The light still moves at c, around 300,000 kilometers per second, 186,000 miles per second, but the metric it is moving through is expanding underneath it. So when you hear radius of the observable universe, 46 billion light years, that is not light had 46 billion years. It is light had 13.8 billion years in a universe that kept pulling everything apart while it ran. The photon mostly loses that race. By the time it finally reaches you, the thing that emitted it is now much farther away than the naive light travel time would suggest. That is why there is a huge difference between how long the light has been traveling and how far away the galaxy is now. Those are not the same number, and if you mix them up, the universe makes no sense. When astronomers say a galaxy is, for example, 10 billion light years away, what they often mean is that its light has been in flight for about 10 billion years before hitting your telescope. That is the look-back time. The photon left when the universe was much younger, but during those 10 billion years, expansion kept increasing the actual distance. So today, right now, the real separation between you and that galaxy can be 20, 30, or more billion light years. In plain distance, you're talking about tens of sextillions of kilometers. That is a number with 21 or more zeros after it. Even at sea, those distances take billions of years to cross, and that's without acceleration, deceleration, or any realistic trajectory. This is the clean, ideal calculation, and it still gives you travel time so long that entire galaxy structures change during the trip. So light is already in trouble. It is finite, and it's trying to work inside a universe that keeps stretching the ruler as it goes. But it gets worse, because on really large scales, expansion does something that makes C look even weaker. On big enough distances, galaxies are not just moving away from you. The space between you and them is expanding so fast that their recession speed, the rate at which they get farther, becomes larger than the speed of light. This does not mean they are locally blasting through space faster than c. Special relativity still holds in their own neighborhood. It means that when you multiply the expansion rate by a huge distance, the effective separation grows faster than light can close it. That creates an entire class of galaxies whose light will never reach you, no matter how long the universe lives. They are too far, and the expansion is too strong. Every photon they emit toward you gets stretched, redshifted, and dragged away faster than it can eat into the distance. It never catches up, so it never arrives. Light is not just slow here, it's completely outmatched by the behavior of space-time itself. This leads directly to the idea of a cosmic event horizon. There is a boundary in the universe beyond which events will never ever send you a usable signal, even in infinite time. Anything that happens beyond that horizon is causally disconnected from you. You cannot see it, you cannot influence it, and it cannot influence you. Those regions might as well be in a different reality because the rules that apply to you simply never overlap with them in any meaningful way. Inside the horizon, light can still win. Very slowly, over billions of years, photons can climb out of the stretching space and eventually reach you. Beyond it, expansion wins forever. The speed of light is not enough to bridge the gap. The universe, in any operational sense, is only the chunk inside your causal reach. Everything else is just a theoretical outside. And that reachable chunk is not stable in the big picture. As time goes on, dark energy-driven expansion pushes more and more galaxies beyond the event horizon. Their light gets redshifted to longer and longer wavelengths, eventually stretched so far that it becomes practically undetectable. They fade out of your observable universe, not because they stop emitting light, but because light cannot keep up with the expanding metric. So, if the universe is already throwing entire galaxies behind a causal wall, if expansion is beating the fastest signal allowed by physics on the largest scales, what does that say about your chances of ever actually talking to most of the universe? Not just seeing it as old light, but sending and receiving information in any direction beyond your tiny local region. You already know the universe is huge and expanding, but here's the part that really locks it down. You're never going to have a real conversation with most of it, not because you're not advanced enough, but because the rules of space-time simply do not allow it. Every way of sending information that physics gives you, radio waves, laser beams, neutrino beams, even gravitational waves, is capped at the same speed, the speed of light in vacuum, roughly 300,000 kilometers per second, 186,000 miles per second. That limit is not an engineering problem. It's built into how space-time works. It's the same constant that shows up in relativity, in how time and space tie together. That means there's a hard limit on what real time can mean. Beyond a handful of light seconds, a few times the Earth-Moon distance range, you'll never have instant back and forth. Not with better antennas, not with stronger lasers, not with alien tech. Nothing. Once you go out to light minutes, light hours, light years, every message you send is old news by the time it arrives. Even a one-bit yes or no answer sent across a galaxy takes millions of years for a round trip. That's what you're dealing with when you think about talking to the universe. So the question becomes, if communication is this throttled, what does that do to causality, to who can affect what and when? Relativity gives you a very clear picture, called a light cone. Take an event, like you watching this video right now. Draw all the points in space-time that light could have reached from the past to get to you, and all the points light can reach in the future. That zone, inside those cones, is what can affect you and what you can affect. Anything outside that region is causally disconnected. No matter what you do, no signal, no particle, no gravity change can jump outside that cone, because that would mean outrunning light. Because C is finite, those cones are narrow. They do not instantly flare out and cover the whole universe. They grow at a fixed rate, 300,000 kilometers per second. So most events in the universe are permanently outside your personal light cone. They never had time to send a signal that reaches you, and you will never have time to send one that reaches them. Most of reality is not just far away, it is in principle unreachable, locked behind a causality wall you cannot cross. So then, suppose there is life in another galaxy, not just across the Milky Way, but in the next major system over. How bad does the delay get there? The nearest big galaxy to the Milky Way is Andromeda, about 2.5 million light years away. That means any signal traveling at sea needs 2.5 million years just to make the one-way trip. If a civilization there pointed an extremely focused laser at the Milky Way and sent a simple "hi," that pulse would cross intergalactic space for 2.5 million years before it even brushes the edge of our galaxy and reaches a detector here. You see that signal, you respond, your hi back then spends another 2.5 million years on the return path. So the total time between them speaking and them hearing your reply is around 5 million years. That is not a delay you can work around. Those are timescales where mountains rise and erode, species appear and go extinct, ice ages start and end. You are not dealing with social timescales anymore. You're talking in geological and evolutionary units. And that is just one neighboring galaxy, not something halfway across the observable universe. If even the simplest two-line conversation across one small intergalactic gap takes millions of years, what does that do to any dream of a connected universe? Could any level of technology actually build a real galactic or intergalactic network under these rules? An internet is useful because latency is low, single-digit milliseconds across a continent, maybe a few hundred milliseconds across a planet. That is what makes video calls, online games, real-time control possible. Now, swap those milliseconds for thousands, millions, or billions of years. That is the latency you get when the speed of light is your upper bound and your distances are measured in light years. No matter how advanced you become, you cannot send information faster than C. You cannot bend that rule with better cables or better protocols. So any network that spans stars, galaxies, or clusters is doomed to feel disconnected. There is no such thing as a live galactic civilization, only scattered islands of life and tech, each running its own history, occasionally exchanging extremely delayed messages that are more like exchange history books than actual communication. And this limitation is not only about light and radio. It hits the fundamental force that shapes structure in the universe too, gravity. Changes in gravitational fields also propagate at the speed of light. If a massive object moves, or two neutron stars merge, or a black hole's configuration changes, the update to spacetime, the gravitational wave, ripples outward at c, not faster. That means the gravitational influence you feel at any moment is based on where things were in your past light cone, not where they are right now, in some global sense. Use the familiar Sun-Earth example again. If, in a purely hypothetical, physically impossible scenario, the sun vanished instantly, Earth would not react immediately. Your planet would continue on its orbit as if nothing had happened for about 8 minutes. It would keep following the same curvature in spacetime, lit by the same sunlight. Then, 8 minutes and 20 seconds after the event, the last photons would arrive, the light would cut off, and the gravitational change would reach you at the same time. Only then would Earth's path start to diverge. So even the fabric of reality, space-time itself, responds with built-in lag, not because it is sluggish, but because C puts a strict bound on how fast cause and effect can spread. All of this leads to one clear conclusion. The universe is not a big, synchronized system where everyone shares the same present. It's a scattered set of local bubbles, each one bound by the speed of light. Most of the cosmos is not just far away, it's outside the range where you can ever trade signals or share information in any practical sense. And if that's how harsh the limit is on communication, even before you try to go anywhere, then the next question is obvious. Why not just break the rule? Why not build something that goes faster than light, a ship, a warp bubble, a shortcut in space-time, and blow past this whole problem? The speed of light is not just a big number you plug into formulas. It's built into how reality itself is wired, and that's why you don't get to simply go faster than it. In Einstein's special relativity, the speed of light in a vacuum is the same for every observer, no matter how fast you're moving. If you're on a spaceship, or on Earth, or orbiting a black hole, if you measure light in empty space, you always get the same value, around 300,000 kilometers per second, about 186,000 miles per second. That's weird if you're used to normal speeds just adding and subtracting. But this number is not just how fast photons move. It acts like a conversion factor between space and time. It ties meters to seconds. It shows up in the basic geometry of space-time. When you draw those light cones we talked about, their slope is set by this speed. Change that number and everything about how cause and effect works changes with it. So the reason everything is constrained by C is not that light is special as a particle. It's that C is part of the structure of the universe itself. So if C is baked into the geometry, not just into one kind of particle, what happens when you try to push something with mass closer and closer to that limit? When you accelerate a massive object, a ship, a particle, even a human in a hypothetical spacecraft, the energy it carries doesn't increase in a simple linear way. At low speeds, doubling your speed roughly multiplies your kinetic energy by 4. That's just basic mechanics. But as you get closer to light speed, relativity kicks in, and the energy required to keep adding speed rises faster and faster. By the time you get to 90% of light speed, 0.9 c, your energy locked into your motion is already more than double the energy you have just sitting still with your rest mass. Push that up to 99% of light speed, 0.99 c, and your energy is more than 7 times your rest mass energy. Each extra 1% closer to C costs more energy than all the previous steps combined. The curve is brutal. If you actually tried to hit exactly C with something that has mass, the math says you would need infinite energy. There is no finite number of joules that gets you there. And infinite energy is not just a lot of fuel. It is literally more than all the stars in the observable universe can provide. So the barrier at sea is not about building better engines. It is a hard stop in the way energy and mass behave in spacetime. So does that mean you are totally stuck for long trips? Or is there any way relativity gives you a cheat code at high speed? Relativity does give you one important effect: time dilation. If you travel at a speed very close to c, say 99% of light speed, your onboard clock ticks slower compared to clocks back home. You still feel normal time. Your heartbeat is normal, your thoughts are normal. 1 second feels like 1 second to you. But when someone at rest compares their clock with yours, they find that less time has passed for you than for them. So a trip that takes, for example, 100 years in the rest frame of the galaxy might feel like only a decade or so on you on the ship. If you accelerate hard, cruise at high speed, then decelerate, you can arrange things so you cross very large distances while you age only a small amount. From your personal point of view, you beat long distances by stretching time, not by breaking the speed limit. But from the outside view, from the universe's perspective, the trip still takes the full decades or centuries. The signal carrying your position still cannot outrun light. Your messages back home still arrive no faster than light signals would. Time dilation helps you survive the journey. It does not let information jump ahead of c. You cheat subjectively, not objectively. The speed limit on cause and effect is still there. So you might say, fine, rockets are bad, chemical fuel is weak. What if you just built something more extreme? Nuclear drives, antimatter engines, constant thrust light sails. Push and push until you punch through c. Is that possible? All of these propulsion systems, real or hypothetical, are different ways of turning energy into motion. They can push you to a higher fraction of light speed. Some concepts might get you to 10, 50, maybe 99% of c if you solved enormous engineering problems, but they are all still playing inside the same geometry. They are all pushing against the same wall. You cannot get a warp effect just by pushing harder on the throttle, because the barrier at c is not a hardware cap. It is a rule about the structure of spacetime. The equations do not say, need better engine. They say, you do not cross this line with anything that carries mass and information. So normal motion through space, no matter how advanced the engine, will not give you faster than light travel. You are still stuck inside the same causal structure defined by c. Put all of this together and you get a very simple but very harsh conclusion. Light remains the cosmic speed limit, and even with all of relativity's tricks, it is still too slow for the universe you're in. Time dilation can make long journeys feel shorter on the traveler's clock, but it does not reduce the actual time other observers measure. It does not let signals arrive earlier than a light beam would. So the delay between events, between one galaxy and another, between one side of the universe and another, is always locked to this finite speed. Stars, galaxies, clusters, and cosmic structures are spread over distances so large that even c turns into a crawl. The universe is enormous, space is expanding, and the fastest possible signal is limited to 300,000 kilometers per second. That combination is enough to guarantee that most of the universe will stay forever out of reach, even for a civilization that can ride right up against the speed limit. And if light is already too slow to tie together galaxies at the level of travel and communication, it gets even more frustrating when you scale down to something you think you control, your own technology. Because the same speed limit that breaks cosmic travel also starts to show up inside your computers and cables, on distances of centimeters and thousands of kilometers, in systems you use every day. You already know light is too slow for galaxies, but it's also starting to be too slow inside the devices in front of you right now. Modern computer chips are only a few centimeters across, under an inch. That sounds tiny, but at the scale of nanoseconds, it's big enough to hurt. Light could cross that distance in roughly 0.1 nanoseconds, a tenth of a billionth of a second. That sounds instant, but it's not. If your CPU runs at around 3 gigahertz, that means one clock cycle is about 0.33 nanoseconds, 1/3 of a billionth of a second. So now look at the ratio. Just moving a signal from one side of the chip to the other can eat 1/3 of a clock cycle, or more. You cannot pretend that's zero anymore. When engineers design high-end processors, they have to think about how far signals travel in one cycle, how many stages they need, how to place blocks on the silicon so that information doesn't need to cross the entire chip in a single tick. This is why you see deep pipelines, multiple cores, caches stacked close to the units that use them, the finite speed of signals, which ultimately trace back to the finite speed of light and the behavior of electrons in the material, puts a hard limit on how fast you can coordinate operations across even a few centimeters. You are not only limited by how small you can build transistors, you are limited by how fast information can physically move across the chip. If light is starting to show up as a bottleneck on a piece of silicon you can hold in your hand, what happens when you scale up to thousands of kilometers, to the cables that connect whole continents? In fiber optic cables, light does not travel at full C. It moves at about 2/3 of that speed in glass, roughly 200,000 kilometers per second, around 124,000 miles per minute. When you send data across an ocean, say about 6,000 kilometers, around 3,700 miles, there's a minimum delay set by physics. Even with perfectly straight fiber and perfect routers, you're looking at tens of milliseconds of round-trip time, on the order of 30 milliseconds or so just from the finite speed of the signal. That baseline is why websites feel slower when the server is on the other side of the world, even if the code is optimized. Even if the data center is powerful, you are still paying the cost of light crawling through glass. Your global internet is literally throttled by the speed at which photons can bounce down those fibers. You cannot compress that to zero. You can only route smarter and place servers closer. If milliseconds matter for regular users, they are life or death for people playing at the extreme edge, like high-frequency trading firms. Between cities such as New York and Chicago, companies have spent hundreds of millions of dollars to lay almost perfectly straight fiber lines. And then, because fiber in glass is still too slow, some built microwave relay networks through the air, where signals can move a bit closer to sea just to shave off microseconds between trading hubs. They care about a few extra kilometers of path length because that translates into a few extra millions of a second of latency, and that is enough to lose money. They are literally fighting over scraps of the speed of light, arguing over tiny fractions of a millisecond, and it is still the same basic limit: distance divided by signal speed. So the speed of light is not just a problem for galaxies. It shows up in finance, in undersea cables, in how fast your apps respond. And it gets even more critical when you look at systems that need precise timing, like GPS. GPS satellites orbit at about 20,000 kilometers above Earth, around 12,400 miles. The signals they send down travel at the speed of light through space, so they take about 0.07 seconds, 70 milliseconds, to reach you on the ground. That does not sound like much, but if you want your position to be accurate to within a few meters, you cannot ignore relativistic effects on the satellite clocks. Those clocks tick slightly faster than clocks on Earth by about 38 microseconds per day due to a combination of special relativity, because they're moving quickly, and general relativity, because they're higher in Earth's weaker gravity. If you ignored that difference and didn't correct for it, your GPS positions would drift by kilometers every day. The map on your phone would be completely wrong. So every time you call a ride, check a delivery, or follow a navigation app, you're using a system that has to factor in the finite speed of light and the relativistic corrections that come with it. Otherwise, it simply would not work at the level of accuracy you expect. The limit at sea is not an abstract idea here. It affects basic navigation on Earth. And when you play online games or join a live call with someone on another continent, a big part of your lag is just photons traveling through fiber, bouncing through routers, crossing oceans. Even if every server was perfect and every packet took the shortest path, you cannot beat the base fact that information can only go as fast as light in the medium. There is no engineering trick that lets you send a signal faster than C, so even on a single planet, the finite speed of light is a real bottleneck for how instant anything can feel. So step back and look at where this leaves you. Light is too slow for instant communication between galaxies, too slow to cross your own galaxy in any reasonable time, too slow to let you talk to nearby stars without ridiculous delays. And now it's starting to be too slow for your own chips and cables and timing systems on Earth. The same limit that wrecks interstellar dreams is already creeping into everyday technology. And if that's what light does to your devices and your networks when everything is close by, what does it do to your view of the universe when everything is far away? It turns astronomy into something very specific. You're not looking at the universe as it is, you're watching old news. You never actually see the universe as it is, only as it was, and that's the catch hidden in every pretty space picture you've ever seen. When you look up at the night sky, you're not seeing stars in real time. You're looking at a history map. A star 1,000 light years away is sending you light that has spent 1,000 years crossing space. So you see that star as it was about 1,000 years ago, around the time of medieval castles and early kingdoms on Earth, not as it is now. Push the distance harder. A galaxy 100 million light years away is different again. Light from that galaxy has been traveling for 100 million years before it hits your eyes or a telescope. That is roughly the time since many dinosaurs still walked Earth. You are seeing that galaxy from an age when your planet's surface, climate, and life looked completely different. Telescopes do not just see far, they look back in time, because light is slow and the universe is big. So every dot you see in the sky is really an old version of something, and that raises a simple question. How old can that footage get when you use serious instruments? Not just your eyes, but space telescopes. Space telescopes like Hubble and the James Webb Space Telescope routinely capture light that has been on the road for 10 to 13 billion years. That means those images are showing you galaxies when the universe was a small fraction of its current age. Young, dense, and very different. Structures were clumpier. Galaxies were smaller or violently merging. Star formation was intense. By the time that light reaches you, the objects that sent it out may be completely transformed. 2 or 3 of those small early galaxies might have merged into a big one. The black holes inside them might have grown. The gas clouds might have formed multiple generations of stars. But you will never see the updated version. You get the 10 billion year old snapshot and nothing else, because you cannot outrun the light to check what they look like now. If even slow evolution over billions of years is locked in old light, what about fast, violent events, like a star exploding? Take a supernova in a galaxy 50 million light years away. When that star explodes, the flash of light starts its journey toward you. 50 million light years means 50 million years of travel for that signal. By the time your telescopes detect that supernova, log it, and put it in a paper or a news article, the actual explosion happened 50 million years ago, long before humans existed. You are just reading the notification now. And while you're watching that one supernova, there are countless others going off right now all over the universe, in galaxies whose light will not reach any observer for tens of millions of years, maybe longer. Those events are real, they are happening, but they are completely absent from every current map because their photons are still in transit, stuck behind the same finite speed limit. So if normal galaxies and supernovae are delayed this hard, what does that mean for the brightest, most extreme objects you see, like quasars? Quasars are insanely bright active galactic nuclei, powered by supermassive black holes feeding on gas, dust, and sometimes whole stars. The ones we see at extreme redshift have light that has been traveling for 12 billion years or more. You were looking at the universe when it was a teenager, less than a couple of billion years old. These are black holes gorging on matter in an era when galaxies were just assembling. You have no idea if those quasars are still active today in the current age. Their fuel could be gone, their brightness could have dropped, their host galaxies might have merged into bigger systems that look nothing like the ones you're seeing. But you are locked into that ancient footage, because that is the light that has had time to arrive. Everything that has happened to those systems in the last 12 billion years is still invisible to you. So step back and look at the whole sky with that in mind. Each direction you look has a different delay, a different look-back time. Near stars are tens to thousands of years in the past. Nearby galaxies are millions of years in the past. Distant galaxies and quasars are billions of years in the past. There is no single universal now in the image. It is a patchwork of different eras laying on top of each other. Because the speed of light is finite and the universe is huge and expanding, you can never see a truly current snapshot of the cosmos. There is no camera you can build, no telescope large enough that will show you what everything looks like at this exact moment. That concept simply does not exist on cosmic scales. Everywhere you look, you are seeing some slice of history, not the present. The sky you see is not a clean map of places. It is a mosaic of times, each point at a different depth in the past. Light is too slow to unify those into a single synchronized picture. Your whole view of reality is based on old signals finally arriving after ridiculous journeys. And once you accept that the entire universe you observe is delayed footage, you hit an even harsher question. If light can barely keep up with what already happened and never shows you everything as it is, what happens when space itself starts moving away from you so fast that even those old signals never arrive in the first place? Galaxies are not just far away. A lot of them are actually being carried away from you faster than light can ever catch up, and that is baked into how the universe expands. On large scales, galaxies are not flying through space in random directions. The overall pattern is that space itself is stretching, and distant galaxies ride that stretch. The farther away a galaxy is, the faster it appears to recede. Astronomers describe this with a simple rule. The recession speed is proportional to the distance. If the Hubble constant is roughly 70 kilometers per second per megaparsec, then for every extra megaparsec of distance, about 3.26 million light years, you add another 70 kilometers per second of recession speed. Stack enough of those megaparsecs, and that recession speed climbs hundreds of kilometers per second, thousands, tens of thousands. Keep going out, and eventually, the effective recession speed exceeds 300,000 kilometers per second, the speed of light. Not because those galaxies are shooting through their local space faster than light, but because the space between you and them is being stretched so strongly that the separation grows faster than any photon can close it. So at first glance, it looks like the universe is cheating, galaxies moving away faster than light. But special relativity says you cannot do that. So what is really going on? Special relativity forbids any object from moving through space-time locally at a speed faster than light. Nothing with mass can zoom past you at more than c in the same local region. That rule still holds. What general relativity allows, though, is for space-time itself to expand. And when you look at very large scales, that expansion can be strong enough that two distant points end up receding from each other faster than c, even though nobody locally is breaking the speed limit. So there are regions of the universe that are receding from you at an effective speed greater than light, and you will never be able to send a signal that reaches them. You cannot aim a rocket or a laser and say, we'll just go faster, because the problem isn't your engine. It's that the metric between you and them is stretching, adding distance faster than you can subtract it. Those regions are being dragged out of causal contact. So what happens to photons that are already on their way from those extreme distances? Can they ever win, or do they simply fall behind forever? Take a photon emitted toward you from a very distant galaxy that is receding superlinearly. That photon starts moving at light speed through the local space around its source. But while it travels, more and more space is created between you and it. The wavelength of that photon gets stretched by the expansion, which is what you see as cosmological redshift. The light shifts to longer and longer wavelengths, lower and lower energy. If the galaxy is not too far, the photon can still, over billions of years, crawl its way into your observable region. But beyond a certain distance, expansion wins permanently. The photon never makes it. Its wavelength stretches toward infinity, effectively washed out into undetectable radiation. The signal is erased, not because light is slow in a vacuum, it's still doing 300,000 kilometers per second locally, but because the universe is zooming out faster than that signal can chase. So you see a clear example of light losing this race when you look at the oldest light you can actually detect, the the cosmic microwave background. The CMB comes from a time about 380,000 years after the Big Bang. Before that, the universe was a hot, dense plasma of charged particles. Photons bounced around constantly. They couldn't travel freely. The universe was opaque. When it cooled enough for electrons and protons to form neutral atoms, space suddenly became transparent, and photons could stream out. That light has been traveling for about 13.8 billion years, and expansion has stretched it from visible and infrared wavelengths down into microwaves, giving you a background glow at about 2.7 Kelvin. You see that glow as a nearly uniform microwave signal across the whole sky, with tiny temperature variations of about 1 part in 100,000. Those fluctuations are the seeds of all later structures, galaxies, clusters, everything. But notice the limit. You can't see earlier with light. The first 380,000 years of the universe are invisible in photons. Light literally cannot show you that period because it couldn't propagate freely then. You are stuck with a snapshot, and everything before that has to be reconstructed indirectly, from theory and from other messengers. So you already can't see the first phase of cosmic history with light, and as time goes on, you lose more, because expansion doesn't slow down. It accelerates. Dark energy, this something driving accelerated expansion, pushes galaxies apart faster and faster on the largest scales. As that continues, more and more galaxies cross your cosmic event horizon. Beyond that horizon, no new light from them will ever reach you. Their photons get stretched to such long wavelengths that they become undetectable, effectively gone. In the very long term, almost all distant galaxies will disappear from view, not because they vanish physically, but because their signals are redshifted into oblivion. In that sense, the universe is erasing its own past faster than light can record it. Right now, you live in a relatively special era. The universe is old enough that structure has formed. Galaxies shine, quasars blaze, and the CMB is still visible, but not so old that accelerated expansion has wiped almost everything from the observable sky. Future observers, tens of billions of years from now, will see far less. Their view of cosmic history will be missing huge chunks that are still visible to you today. So, on the largest scales, you have a universe where the fastest possible signal loses to the growth of space itself. Distant regions slide permanently out of contact. Early history is hidden behind opacity, and late-time history is redshifted away. Light is not just slow here, it is outclassed. And if light is getting beaten this badly by expansion, it is natural to ask, is there any other messenger that can do better? Maybe neutrinos? Maybe gravitational waves? Maybe some other field? Or are they all trapped in the same speed limit club with exactly the same cap? You don't escape the speed limit by switching from light to some other kind of signal. Everything that can actually carry information is trapped in the same club. Start with neutrinos. They're famous for being ghost-like. They barely interact with matter. Trillions of them pass through your body every second without touching anything, and they move incredibly fast, but they still do not beat light in vacuum. Neutrinos have a tiny but non-zero mass. That means, by relativity, they must travel just under the speed of light, not equal to it, not faster than it, always a hair below. You can see how this plays out in extreme events, like the supernova SN 1987A. When that star's core collapsed, detectors on Earth saw a burst of neutrinos a few hours before the visible light from the explosion became bright in the sky. At first glance, it looks like neutrinos arrived first, like they are faster, but that's not what actually happened. The neutrinos escaped directly from the collapsing core. They streamed out almost immediately because they don't interact much with the dense outer layers of the star. Light, on the other hand, had to fight its way outward, bouncing around inside the star's material, taking time to diffuse to the surface. Only after that delay did the photons finally break free and rush out through space. Once both signals were in vacuum, neutrinos and photons were essentially tied at the same speed, c. The earlier neutrino detection was about where they came from inside the star, not about breaking the universal limit. So neutrinos are incredibly fast, but almost c is not good enough to change the cosmic communication problem you're facing. Then there are gravitational waves, ripples in space-time itself. If anything had a chance to dodge the rules, you might think it would be those. But measurements say no. They are locked in too. In 2017, detectors picked up a gravitational wave event called GW170817, caused by two neutron stars merging about 130 million light-years away. Almost at the same time, space telescopes saw a gamma-ray burst and other electromagnetic signals from the same region. When scientists compared the arrival times, the gravitational waves and the light had reached Earth within just a couple of seconds of each other, after traveling for about 130 million years. That is insanely tight agreement. Over that distance, a tiny fractional difference in speed would have produced a huge time offset. But instead, they showed that gravitational waves and light travel at essentially the same speed, c. Even ripples in spacetime are stuck obeying the same limit. There is no gravity wave shortcut that lets you send a faster message across the universe. So you check light, neutrinos, gravitational waves, and they all line up on the same maximum speed. If there was some hidden messenger that could go faster, what would you expect to see? If a real faster-than-light signal existed, one that could carry information, you'd see causality break. You would find events that look like effects happening before their causes. Strange patterns in particle physics where signals show up before they are sent. Violations of basic symmetries that modern theories rely on. Astronomers would see weird timing in explosions and pulsars and cosmic rays, where something clearly outruns all the known channels. So far, every precise test in particle accelerators and cosmic ray observations and timing of supernovas and mergers lines up with the same story. Information never outruns light in vacuum. Whenever people have claimed a possible exception, it has collapsed under better data or experimental corrections. The speed limit keeps holding over and over. At this point, someone usually brings up quantum mechanics, and especially entanglement, because that looks like instant, distance-independent connection. So does that break the rule? Can you use that as a faster-than-light phone? Entangled particles do show correlations that appear instantly, no matter how far apart they are. Measure one, and the state of the other is linked in a way that seems instantly to ignore distance. But the key detail is this. You can't control the outcome of your measurement. Each result you get is fundamentally random. You only see the strange correlation when you compare the data from both sides using a normal light-speed signal. Because you can't choose the result on your side, you can't encode a message in it. There's no way to rig the randomness to send a yes or no to the other particle. The no signaling theorem in quantum theory is very clear on this. Entanglement does give you weird, non-classical correlations, but it does not give you a communication channel faster than light. You get quantum strangeness, not a shortcut through spacetime. So, step back. Photons, neutrinos, gravitational waves, any real causal signal, they're all capped at c. Every candidate messenger plays by the same rule. What that tells you is that the universe is not slow because you picked the wrong type of signal. It is slow because space-time itself enforces the limit. The speed limit is universal and universally frustrating. It shapes everything, from when you see a supernova to how long it takes a rover command to reach Mars, to when gravitational waves from a merger arrive, to when entangled particle experiments must be interpreted. Every attempt to send information is trapped under the same cap. And that brings you to the last hope people usually cling to. If you can't send a signal faster than light through space, maybe you can cheat by changing space itself. Bend it, punch a tunnel through it, build a warp drive or a wormhole and step around the limit instead of trying to brute force through it. If you can't beat the speed of light by going faster through space, can you cheat by editing space itself? Bending the board instead of running across it. That's the idea behind things like the Alcubierre warp drive, at least on paper. Instead of pushing a ship through space, you contract space in front of it and expand space behind it. The ship sits in a kind of bubble, and the bubble moves locally. Inside that bubble, nothing is breaking the speed limit. The ship just kind of floats, but from the outside, the whole bubble can move effectively faster than light relative to distant objects. On a whiteboard, it looks clever. Relativity allows space-time to stretch and squeeze, and you're just telling it to do that in a controlled way. Compress here, stretch there, surf the wave. This gets around the rule nothing moves through space faster than c, because you're not doing that, you're moving space itself. The problem is what you need to build that wave. The math says you need exotic matter with negative energy density, stuff that does the opposite of normal gravity. Instead of attracting, it would repel. And you don't just need a tiny amount. Rough estimates say the energy required is enormous, often comparable to the mass energy of stars. We don't know how to make even a gram of stable negative energy matter, let alone star-level quantities. So a warp drive right now is not difficult engineering, requires a kind of substance the universe might not even allow in macroscopic amounts. And even if you somehow had that material, you'd have control problems. How do you turn the warp bubble on and off? How do you steer it? How do you stop without crushing or roasting everything inside? The original Alcubierre solution doesn't come with a user manual. It's a mathematical curiosity, not a real spacecraft design, at least with the physics we understand today. So if bending space in a controlled wave is that extreme, what about taking a shortcut through space? Just punch a tunnel and skip the distance. That's where wormholes come in. General relativity does admit solutions that look like tunnels connecting two distant regions of spacetime. In principle, if you had a stable traversable wormhole, you could enter on one side, exit on the other, and bypass light years of normal travel. From an outside point of view, you've crossed a distance faster than any beam of light going the long way around. But again, the details are brutal. To keep a wormhole throat open so it doesn't pinch shut instantly, you need, once more, exotic matter with negative energy. And not just a sprinkle. You need enough to counteract the tendency of gravity to collapse the tunnel, and you have to arrange it with insane precision. On top of that, most wormhole solutions look violently unstable. Tiny perturbations, small amounts of normal matter falling in, even stray radiation can cause them to collapse or form horizons that trap anything inside. Right now, there is no known way in real physics to construct, stabilize, or naturally maintain a traversable wormhole large enough for a spaceship. The ones we can write down easily on paper either close too fast, require impossible energy conditions, or come with other pathologies that make them useless as transport devices. They're great for thought experiments, but when you ask, can we actually build one, the answer with current theory is basically no. And even before you dream about engineering, there's another layer of trouble. Quantum field theory does not like large amounts of negative energy just sitting around where you want it. Quantum inequalities and related constraints tell you that you can't have arbitrary amounts of negative energy for arbitrary long times in arbitrary regions. There are trade-offs. If you get a burst of negative energy in one place, you're forced to pay it back with positive energy elsewhere, on timescales and distances that limit what you can do. The specific, large, stable negative energy densities needed for warp drives and traversable wormholes seem to violate these quantum constraints. In simple language, the universe doesn't like the kind of stuff you need for faster-than-light hacks. The same quantum rules that allow small, temporary negative energy effects, like in the Casimir effect, slam the door on scaling that up to whole spaceship rides a wave of negative energy. At least based on everything we know right now. But suppose for a moment that someone found a way around all those energy problems. A theory that actually allows a warp drive or a wormhole. There's still one more wall to deal with: causality. Most faster-than-light concepts, if you plug them into relativity carefully, let you set up scenarios where signals loop back in time. In some reference frames, your message arrives before you send it. You get effects happening before causes. You can create closed time-like curves, paths through space-time that let you come back to your own past. That opens the door to paradoxes, kill your grandfather-style problems, and breakdowns of logical order. Any physically allowed faster-than-light mechanism would have to somehow avoid these causality violations, or hide them behind horizons where they can't affect the outside world. So far, nobody has a clean way to do that. Every time you try to let information outrun light in a way that interacts with normal spacetime, you end up punching holes in cause and effect. And that's a huge red flag. Put all of this together and you get a blunt conclusion. With the physics you have today, you're stuck with slow light, practically speaking. Until we find genuinely new physics that radically changes our understanding of spacetime, energy, and causality, all serious models say the same thing: no information outruns c. Warp drives and wormholes are not just hard, they require ingredients and behaviors that everything else in physics seems to forbid or punish. Your galaxy-hopping starships in a single human lifetime, your instant jumps across millions of light years. All of that crashes straight into the speed of light and the structure of space-time behind it. And while we hit this wall when we try to go outwards to other stars and galaxies, there's another place the limit shows up in a different way. When you look backwards in time, toward the beginning of everything, there's an entire era of the universe you will never see directly, not because light is mathematically impossible to escape, but because light itself was physically unable to escape back then. In the very early universe, before about 380,000 years after the Big Bang, everything was a super hot soup of protons, electrons, and photons. The temperature was so high that electrons could not stay attached to protons. Anytime they tried to form atoms, collisions and radiation would rip them apart again. The result was a plasma, a charged fog where photons were constantly crashing into free electrons and changing direction. In that plasma, light could not travel freely. Photons didn't get clean, straight paths. They bounced, scattered, and were reabsorbed over and over. That means no light from that era can reach you directly today. There is no view of the universe from those first hundreds of thousands of years using ordinary photons. The cosmos was literally opaque. Only when the universe expanded and cooled enough for electrons and protons to finally stick together and form neutral hydrogen, a process called recombination, did the fog clear. Once neutral atoms formed, photons were no longer constantly scattered by free electrons. Suddenly, light could travel long distances without being blocked. That is the moment the universe became transparent in the sense you recognize now. So your visible universe, in the literal sense, only starts after that cooling transition, before recombination. Light is locked inside the plasma. It cannot carry an image from that time to your detectors. You hit a hard wall in the early timeline. The oldest direct light you do see is what you call the cosmic microwave background, and it really is like the first photo the universe ever took of itself. The CMB is made of photons that last scattered around that recombination era, roughly 380,000 years after the Big Bang. Back then, that radiation was more like visible and infrared light. But as the universe expanded over the next 13.8 billion years, the wavelengths got stretched, redshifted, down into the microwave range. Now you see it as a faint, almost uniform glow across the whole sky, with a temperature of about 2.7 degrees above absolute zero. If you zoom in on that glow with sensitive instruments, you find tiny temperature differences, about 1 part in 100,000. Those tiny fluctuations are crucial. They mark places where the density was slightly higher or lower than average. Those small differences grew over time under gravity into all the large-scale structure you see today. Galaxies, clusters, filaments, voids, the entire cosmic web. But there is a hard boundary here. That CMB surface is as far back in time as light can show you directly. Photons can't give you an image from before that last scattering moment, because earlier photons never traveled freely, they were trapped in the plasma. So even with an infinitely good telescope, you cannot see past that wall with light. It's a strict observational limit. You might ask, if light can't reach back earlier, are there other messengers that can? Something that slipped out before the universe turned transparent for photons? In theory, yes, there should be a cosmic neutrino background, a sea of neutrinos left over from about 1 second after the Big Bang, when the universe was still extremely hot and dense, but already more open to these weakly interacting particles. There might also be very faint gravitational wave backgrounds produced even earlier by violent processes in the young universe, or by inflation itself if it happened. The problem is detection. Those relic neutrinos are now incredibly low energy, spread thin across space, and your detectors are nowhere near sensitive enough to pick them up directly. They mostly just pass through everything without a trace. The gravitational wave background, if it exists in the way models suggests, would have amplitudes way below what current observatories can detect. They're tuned for strong events like black hole and neutron star mergers, not the faint noise of the entire early universe. So practically, light remains your main tool, and light starts late, hundreds of thousands of years after the Big Bang. Everything before that has to be reconstructed indirectly by matching models to the patterns you see in the CMB and in the later distribution of galaxies. That's where ideas like cosmic inflation come in, a period of extremely rapid exponential expansion very soon after the Big Bang. Inflation, if it happened, would stretch tiny quantum fluctuations to cosmic scales, seeding the slight density differences we now see imprinted in the CMB. You can look for specific patterns in that background, like particular shapes in the temperature fluctuations and polarization, as indirect evidence of what inflation did. But notice what you're doing. You are not watching inflation itself. You're reading its fingerprints in data that come much later. The detailed behavior of the universe in the first fractions of a second, or even the first few minutes, is encoded in a messy way through nuclear reactions, plasma physics, and later structure growth. Photons cannot cross the early opaque plasma to give you a direct view. They only show you the aftermath once things cool enough. That means the earliest moments of the universe, any before that you imagine close to the Big Bang, are hidden behind a literal optical wall. The universe's baby pictures are blurred and blocked by its own early conditions, and you can only guess the details by reverse engineering the traces left behind. Put the key facts together. Light does not move infinitely fast. It takes time to get from there to here, and the early universe was opaque to light for hundreds of thousands of years. Combine those and you get a permanent observational boundary. No telescope, no matter how large, no detector, no matter how advanced, will ever take a direct image of the first instant of the universe, or even the first 380,000 years. The finite speed of light plus the physics of hot, dense matter guarantee that part of reality is always out of reach. Some parts of cosmic history will always be inferred, modeled, and debated, but never seen. There is a hard line in the past beyond which photons cannot report back to you. And while the early universe hides behind that wall, the far future has its own kind of erasure. As expansion keeps pushing galaxies beyond your horizon, the night sky itself will change, and most of what you can see today will quietly fade away from view. The night sky you know is temporary, and in the long run, it will almost completely empty out. Not because stars die, but because light can't keep up with the way the universe is stretching. Right now, when astronomers look at distant supernovae and at the cosmic microwave background, they see clear signs that the universe's expansion is not just continuing, it's accelerating. The distances between galaxy clusters on very large scales are growing faster and faster. The driver for that, whatever it really is, we call dark energy. It behaves like a kind of energy built into space itself. As space expands, there is more of it, and its effect doesn't dilute the way normal matter does. On small scales, like inside the Milky Way, gravity wins. Stars and gas stay bound together. On very large scales, dark energy wins, and galaxy groups are pushed away from each other. As time goes on, galaxies that are not gravitationally bound to us recede faster and faster. That means more and more of the universe crosses the event horizon we talked about earlier. One by one, entire galaxy clusters slip into a region where no new light from them will ever reach you. So, the longer the universe runs under dark energy, the more of it disappears from your causal reach, simply because expansion outruns the finite speed of light. And that has a brutal consequence for what the future night sky will look like. Fast forward billions of years, the Milky Way and the Andromeda galaxy will likely have merged along with some of the smaller galaxies in our local group into one giant elliptical galaxy. Gravity inside this local bubble is strong enough to hold things together, but everything outside that group, all the other galaxies you can see now, will keep receding and redshifting. Given enough time, their light shifts to longer and longer wavelengths, gets dimmer and dimmer, until it's effectively undetectable. You end up with a sky where the only visible galaxy is the merged remnant of the local group. Everything else is gone from view, not because those galaxies stopped existing, but because their photons can no longer reach any observer here. Future astronomers born in that era will look up and see a universe that feels small and quiet. One big galaxy, some stars, maybe some local structures, but no vast universe full of other galaxies stretching to the horizon. They will see almost nothing beyond their own gravitationally bound system. Their observable universe will be a tiny island, and they will have no reason from direct observation to think anything else is out there. Now, think about what that does to cosmology, to trying to understand where everything came from. Today, you can measure the Hubble expansion by looking at how galaxy redshifts change with distance. You can see the CMB as a leftover glow from a hot, dense early universe. You can combine those with other data and infer a Big Bang origin. In the far future, all of that goes away. The cosmic microwave background gets stretched to wavelengths so long and so weak that it blends into noise, effectively impossible to detect. External galaxies fade out, leaving no redshift pattern to study. Future scientists in that isolated galaxy will not see a universe that clearly expands. They will not have a visible CMB to point to. They will not see a universe full of external galaxies rushing away. They will likely conclude they live in a static, eternal island universe, a large, long-lived galaxy floating in empty space. Almost all the clues we use today to reconstruct cosmic history will have been erased from their sky by expansion outpacing light's ability to deliver information. Every distant photon that could tell them the universe is expanding, it used to be hotter and denser, it started in a very different state, will have been redshifted to absurdly long wavelengths, the signal buried under other sources or effectively gone. The evidence is available to you now only because you live at an in-between time. The universe is old enough for structures to exist, but not old enough that dark energy has scrubbed almost everything from view. So light is too slow to preserve the record. It cannot keep the proof of the Big Bang and cosmic expansion accessible forever. The expansion stretches those photons faster than new ones can arrive in useful form. As the universe gets older, the amount of direct information available about its own past actually shrinks, even though the total volume of space keeps growing. That leads to a strange conclusion. In a cosmos where the speed of light is finite and expansion keeps accelerating, there is only a limited window of time when intelligent observers can actually do modern cosmology the way you know it. You are in that window right now. You live in an epoch where you can still see the CMB, still see distant galaxies, still see large-scale structure over billions of light years. You can measure expansion, infer dark energy, build a consistent picture of a hot, dense beginning and an expanding, cooling universe. In a few tens of billions of years, that entire framework will be hidden from view. The universe will still exist, stars will still burn, planets will still orbit, but the story it tells through light will be almost completely gone. So you have a speed limit that is too slow to connect galaxies, too slow to cross your own galaxy in any practical time, too slow to keep up with expansion, too slow to preserve the clues about the beginning, and yet it is still the fastest anything can go. On human scales, it looks insanely fast. On cosmic scales, it barely does the job at all. The only thing left now is to put all of this together. Human versus cosmic scales, communication versus causality, early universe versus far future, and face the full punchline. The speed of light is the ultimate limit that makes physics work, and at the same time, it is laughably, painfully slow for the size of the universe you're trapped in. 300,000 kilometers per second sounds unbeatable until you put it next to the universe it has to cross. On human scales, light is ridiculous. It does about 300,000 kilometers every second, around 186,000 miles per second. Your fastest passenger jets cruise around 900 kilometers per hour, roughly 560 miles per hour. Your fastest probes, like the Parker Solar Probe, hit a few hundred kilometers per second near the sun. Compared to sea, all of that looks like slow traffic. Jets and rockets might as well be parked. But your local reality is tiny. Your own galaxy's disk is about 100,000 light years across. Your observable universe has a radius around 46 billion light years and a diameter around 93 billion light years. Stack 300,000 kilometers per second against tens of billions of distances and billions of years of expansion, and suddenly this ultimate speed is painfully slow. It can't cross your galaxy in a human timeframe. It can't keep your universe in causal contact with itself. It can't even preserve its own history indefinitely. So here's the situation you're really in. Every star, every galaxy, every cluster is trying to interact in a kind of laggy multiplayer universe, and the server tick rate is hard locked to the speed of light. No one, anywhere gets real-time updates about anyone else. When you look out, you see other galaxies as they were millions or billions of years ago, not as they are right now. When some other civilization, if it exists, looks at you from far away, they see Earth's past, not your present. Most potential players are outside your causal lobby altogether. You can't invite them, you can't ping them, their light hasn't had time to reach you, and your light hasn't had time to reach them. There is no patch, no upgrade, no low latency mode you can unlock with better technology, radios, lasers, neutrino beams, gravitational waves, hypothetical warp concepts. They all run into the same problem. Information cannot outrun C. The universe is permanently running on the slowest tick rate that still keeps causality intact. That leads to a brutal, simple rule for what counts as real for you. Your picture of the universe is literally just a set of photons that have had enough time to arrive where you are. Change your time, change your position, and your observable universe changes with you. Move 1,000,000 light years and a different shell of galaxies comes into view. Wait 1 billion years and some galaxies you see now will have faded beyond detection, while others that were too faint or too far might enter reach. Because C is finite, reality is local and delayed. The universe you talk about is never the whole thing. It is just the region that has managed to send you usable signals within the age of the cosmos. So the universe you see is not what is, it's what has arrived. Your night sky is a curated, outdated feed of events filtered by distance, expansion, and this speed limit. Different observers scattered through space-time see different versions of the universe, and none of them get the full current story, because there is no way to sync it all up. Here's the deepest irony in all of this. The speed limit that makes physics work is exactly the thing that makes large-scale exploration almost impossible. If C were infinite, relativity would fall apart. Time and space wouldn't mix the way they do. Cause and effect would be a mess. You could have instant influences crossing any distance with no delay, and a lot of the structure of modern physics would stop making sense. The finite speed of light is what gives you light cones, protects causality, and lets you build a consistent model of events. It is the backbone of both special and general relativity. But that same limit is what makes interstellar travel a multi-decade or multi-century project, even at extreme speeds. That same limit is what turns intergalactic communication into a 1,000,000-year round trip. That same limit is what guarantees that most of the universe will always be outside your light cone, forever unreachable. The universe works because light is finite, and the universe is unreachable for the exact same reason. So when you hear nothing can go faster than light, do not picture a universe where light is some unstoppable racer stitching everything together. Picture a universe so huge, so old, and expanding so fast that even the fastest possible thing can barely shuffle between nearby stars, takes 100,000 years to cross its own galaxy, and can never, ever send a signal to most of what exists. The speed of light is not just a limit, it defines what parts of reality you can ever see, touch, or talk to. On human scales, it feels absurdly fast. On cosmic scales, in a universe this big, it's kind of a joke. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.